Good morning, everyone. First, I would like to. Do you hear me? Yeah. First, I would like to thank Professor Osman for having me over. Today, I would like to share with you some of my latest research on risk modeling and analysis. The title might actually be a little bit misleading in the sense that we start with bankruptcy, distress, and credit risk prediction. This is, for me, is just an application. So I'm not going necessarily to focus on the application, but rather on the methodological framework that I'm proposing here. So what I propose as a way to go forward is this. We'll start with stressing out the research motivations behind what I'm proposing here. The landscape, very briefly, I will present the landscape of research on bankruptcy, distress, and credit risk. Then we'll go with the proposal of a generic prediction framework with plug-and-play implementation options, and I will discuss the implementation decisions. And finally, I will show some numerical results to illustrate or to show the performance of the model with an application here in bankruptcy prediction, and I will conclude. So I don't actually have to sell to you the idea of artificial intelligence being an important tool these days. My colleagues yesterday and the day before have done a good marketing for it. What I would, however, like to stress out is that in terms of the design of classifiers, lately very little has been done, methodologically speaking, so most of the research is based on the identification of drivers or explanatory variables. In this research, I'm rather focusing on the design of classifiers. You can't hear me like this? Right, sorry, I'm not used to the defaults. Right, so in terms of research motivations, three main research motivations for me. First one is the scarcity of multi-criteria decision-making based methodologies or classifiers, which are non-parametric. The scarcity of non-parametric classification frameworks which perform both in-sample and out-of-sample classifications. And finally, the inconsistency in the choice of the relevant performance measures and their implications on the choice of cutoff points and the performance of classifiers. So let me be a little bit more specific. In terms of the scarcity of MCDM-based non-parametric classifiers, actually, in the whole MCDM literature, there is only one paper that claims that it proposes classifier. It's a Topsys-based classifier, but there are no details whatsoever on how the classification is made. Topsys is basically a method for ranking rather than classification. So basically, there is a shortage out there, or as far as I'm concerned, there are opportunities for designing new classifiers there. Most of the non-parametric frameworks, and to be more specific, the MCDM ones, actually only perform in-sample predictions. So there are, they don't necessarily test out of sample, and they don't necessarily provide any details on how out-of-sample evaluation is or predictions are made, which is another thing that I am covering here. And finally, one of my biggest concerns when it comes to the design of classifiers or prediction models in general is the choice of the performance criteria. Most of what people are doing basically in this area has to do with the identification of drivers. So basically, what they are doing is that they're using standard software, and the standard software is using standard methods for optimizing or the parameters of the model. And the performance criteria that they are using for the optimization problem most of the time, as far as I'm concerned, are inconsistent with the objective of the classification. So that's another issue that I'm trying to address in here. Right, so just to paint very briefly and at a very high level the landscape of research on bankruptcy, distress, and credit scoring, or credit risk. There are basically 6 streams. First one is concerned with the design of prediction models or classifiers. Second one is with the design of the estimation methodologies for the parameters of the models. The third one is concerned with the performance criteria and measures. Obviously, there is a linkage between all these. The fourth one is on the performance evaluation of prediction models. As you all know, when it comes to the performance evaluation of prediction models, typically people are selecting a number of criteria and their measures, and then they are basically ranking the models based on a single measure at a time. Problem with an approach like this is that a model might perform very well on one criterion or measure and very poorly on another one. So there is no consistency in terms of the rankings. To the best of my knowledge, I'm the only one actually with my team, mainly PhD students, who have done research in this area to propose multi-criteria frameworks for the performance evaluation of prediction models. If you want to have more information on this, you can just Google my name and you will find a number of papers addressing both the performance evaluation of forecasting models of continuous variables and of discrete variables in the case of risk modeling analysis. The fifth stream is about the identification of the most effective drivers. A lot of research actually is going on in this area, especially at stages where the fields seem to be stuck or saturated. People are looking for more innovative drivers of risk. And the last one, last stream has to do with issues affecting the performance of models, and that includes sampling and different types of implementations and percentage of bad good cases in the sample, and so on and so forth. Right, so obviously all these are interrelated if we look at the methodological steps of a typical prediction exercise. I will be focusing on the first stream. I'm concerned with the first stream in this presentation. And here I'm just proposing one possible classification. One can classify prediction models into static and dynamic, or into non-parametric and non-parametric. So this is the one that is more relevant to the talk. So in terms of parametric models, we have the usual ones we are all familiar with. Statistical models such as multivariate discriminant analysis. We have probability models such as logic, probability, and so on. And then we have stochastic models such as survivor analysis models, the hazard models, for example. And then in terms of non-parametric models, we have mathematical programming-based ones, such as the mathematical programming version of the multivariate discriminant analysis. We have data envelopment analysis. And in terms of artificial intelligence models, we have artificial neural networks, support vector machines, genetic algorithms, case-based reasoning, and so on and so forth. In terms of the MCDM models, to the best of my knowledge, the only ones available are the ones I proposed. One missing there, EDAS, TOPSIS, and the double reference points method. And just actually a couple of days ago, another paper has been accepted on another method called VPER. Right, so for those who are not necessarily familiar with the classification, distinction or the difference between the parametric and the non-parametric ones is the fact that lies in the fact that for the parametric models, we are basically making a number of assumptions about the distribution of the data, whereas in the case of the non-parametric ones, there are no assumptions, and that's obviously, from a practical perspective, less of a hassle. Right, so let me just stress out here something that is important. A lot of people are in different areas in terms of applications. Some working on bankruptcy, some working on distress, some are working on credit scoring, others are working on all sorts of other classification problems. For example, classifiers to identify cases of cancer, and so on and so forth. The modeling frameworks are common to all of them. Okay, you know the methodology, you can apply it just anywhere. The main difference lies in the choice of the drivers in terms of the specific application you are dealing with. So for the students in the audience, just learn the methodology. In terms of applications, you will learn about the application area and then just choose the relevant drivers. Right, for today, my proposal is the following. I'm proposing a generic prediction framework. I'm calling it generic because I want it to be more of a plug and play type of framework where depending on the application area and the tools that are available to you, you might just plug, make a number of decisions or plug choices in the framework and the framework become operational. So let me go a little bit in detail into the design of the framework. Given a data set, typically what we do is we divide the data set into two subsets, a test or training sample and a training sample and a test sample. So what I'm proposing here in terms of the in-sample analysis is to compute multi-criteria decision-making scores using a specific method of your choice. Once you have those scores, you use a classification rule basically to predict the risk class for the training sample. And then you have the observed risk class. You compare the two and compute the relevant performance statistics that you choose for the purpose of your exercise. And then we use the predicted risk class obtained with the MCDM method to train the out-of-sample classifier. And then we will predict the risk classes for the test sample. Again, we have the observed or actual risk classes for the test sample. We compare them, and then we compute the relevant performance statistics. This is basically, there's nothing new actually here, right? What is new is the choice of, or how we make decisions in terms of what we put where. Right, so let me emphasize the implementation decisions here. I'm classifying them into mainly four. Choice of in-sample classifier, choice of out-of-sample classifier, choice of performance criteria and their measures, and the choice of the drivers. So in terms of the choice of the in-sample classifier, and this is the novelty in what I'm presenting here, I came up with a list of, I think 17 or something, methods, new methods, that I classify into three categories: methods exploiting basic scores, methods based on a benchmarking framework, and methods based on pairwise comparisons. So basically, these are the methods. Some of them, like EDAS, TOPSIS, the double reference point method, and Vicker, have been published. The remaining ones are actually in the process of being published. They are submitted for publication. Right. So when I say a plug and play framework is in the sense that, okay, you can choose any one of these options, okay, as an implementation choice. For those of you who are interested in the actual technical details, you can maybe take a picture of this or just Google my name and you will find out. Right. Now, we are not done in terms of the choice of the in-sample classifier. Still a number of questions here to be addressed. Which decision rule to use for classifying alternatives in the training sample? into the relevant risk classes. In our case, because of the application I'm considering here, bankruptcy. So first of all, we need to come up with a cutoff score. And second, we need a classification rule. So the classification rule basically is the following. If the score of an observation, a company, for example, is less than or greater than, depending on whether the score has to be maximized or minimized, then we assign the entity or the observation to the risk class of risky. Otherwise, it is non-risky. So nothing really new. Okay, just packaging. What is new here, however, is the first part. Okay, and this is crucial. How to optimize the choice of the cutoff point. And this is what I am proposing here for the optimization of that cutoff point. So there is an algorithm here. The input to the algorithm is a performance measure. I will be talking about performance measures later. And a nonlinear programming search algorithm chosen according to the properties of the measure, performance measure, along with the MCDM scores of the in-sample alternatives. So the method basically consists of two steps. First one consists of computing lower and upper bounds that define an interval within which we will be searching for the optimal cutoff score, optimal with respect to the chosen performance measure. And then we will perform a search within that interval, and the search is basically done using a nonlinear programming algorithm. And some of the simplest ones to use and most effective are the golden section search and the Fibonacci search. Here I would like just to stress out that during the search, for each potential cutoff score or value within the search interval, we have to actually assign the different observations to different risk classes and compute the relevant statistic. So output, the optimal cutoff point along with the corresponding predicted risk class. Right. Now, in terms of, okay, if you have questions, you can ask me as we go along, because this is one of the main things that is driving the performance of the framework. Right.
Why don't we have fix the performance measure?
Yeah.
And fix the average and plus minus one standard deviation.
Yeah.
Spoke about it before, and it's easy to understand. So once you have the whole measure,
Yeah.
then you have the average, the standard deviation.
Yeah.
And then take a cutoff point, maybe two standard deviation, two standard deviation.
Yeah.
That really accurate.
Yeah.
So depends on that cutoff percentage.
That's one way of doing it. Okay. That's one way of doing it. I have chosen to do it this way, and it's paid off. Yeah, as simple as that. But there are many different ways in which it can be done. Right. The next decision is about the choice of the out-of-sample classifier. In this situation, basically, I am using an instance of the case-based reasoning, namely the k-nearest neighbor algorithm. Right, with this algorithm, k is the size of the neighborhood, and I'm testing for several values, and I'm also using a number of distance metrics here to see what is the impact on the performance of the classifier. And finally, we have as a classification criterion, the majority vote here. So I'm assuming that if you are familiar with the field, all this stuff is actually straightforward. Right, so I'm not going to go through the details of the algorithm. Right, we talked about the performance, both in sample and out of sample, and most importantly, I talked about the choice or the optimization of the choice of the cutoff score based corresponding to a given performance measure. We have done a literature survey on performance criteria and measures in the field, and we came up with this classification. By the way, the classification is not standard. This is what we are proposing here. So there are basically criteria called reliability, costs, benefits, complexity, universality, and ability to incorporate managerial judgment. And in terms of the reliability, we have a number of sub-criteria: theoretical relevance or relevance by design, validity of the model or method, accuracy, and stability. And for the sake of what we are doing here and the empirical bit, I am going for accuracy. Right, in terms of measures for accuracy, they are divided into two main categories, three main categories: discriminatory power, calibration accuracy, and correctness of categorical prediction. And in this specific research, I'm focusing on the correctness of categorical prediction, and to be more specific, I'm choosing type 1 and type 2 errors, sensitivity and specificity as the relevant measures used to judge the models, but also to optimize the choice of the parameters of the cutoff score. Right, drivers. Again, as I said, the drivers depend on the application. I'm not going to go through the survey of the literature on the drivers for bankruptcy, distress, and credit scoring. Here, all what I'm concerned with is to show how the proposed framework is performing, and so I'm just picking here the multivariate discriminant analysis model of Toffler, which according to an extensive research that we have, empirical investigation that we have done, this one is always among all the models that we have considered, and we have considered plenty of models in different categories. This one is always amongst the best ranked ones, yet it's very simple. So we have picked actually this one, and we reworked this model in our framework. The model basically is limited to the use of liquidity drivers, and the drivers are basically the following: current liabilities to total assets, and this is obviously to be minimized, so the lower the value, the better, and current asset to total liabilities, profit before tax to current liabilities, and no credit interval, and these are to be maximized, so the higher the value, the better. Now, in terms of the empirical investigation, we have considered firms listed on the London Stock Exchange. So basically what we have here, we have considered the time window of 2010-2014, a total of 6,605 firm year observations, consisting of both bankrupt and non-bankrupt firms, and we excluded the financial firms and utilities. The list of the, okay, in terms of bankruptcy, okay, it's a matter of definition. How do you define bankruptcy? There is no consensus. Most of the research, however, on bankruptcy have considered this, these criteria. So basically codes 16, 20, and 21. And here we are basically doing what everybody is doing in the field. So we are not innovating on this. This is one of the commonly accepted definitions of bankruptcy. Right, some statistics. This is important. The percentage of failed firms or bankrupt firms in the sample is 6.16%, and non-bankrupt ones 93.84% for a total of 100%. Right, we know from experience and also from previous research that the percentage of bad cases, in this case we are talking about failed firms or bankrupt firms, affects in a non-negligible way the performance of the models, right? With non-parametric methodologies, this is less of a case, however. So in terms of experiments, basically we considered 30 pairs of training and test samples. They were randomly generated without replacement. And the size of the training sample is twice the size of the test sample. So these are common decisions made. Right, let's get to the performance. So if we consider the multivariate discriminant analysis model of Taffler, and we look at the in-sample performance, we see that on average, for T1, the type 1 error, so basically percentage of bad cases that have been predicted as wrongly, we have 98.82%. For the good cases that have been badly predicted or wrongly predicted, 0.26%. Good sensitivity, so bad cases correctly predicted as bad cases, 1.18%, and specificity is good cases correctly predicted, so 99.74%. This is in sample. So in principle, a model like this, in terms of correctly predicting the non-failed firms, is doing a very good job by forecasting standards, but in terms of predicting the bad cases, it's doing poorly. All right. Well, doing poorly. This is clear. So when we get to the out-of-sample performance, obviously we have 82.20% of the bad cases are wrongly predicted. The good cases, 17.01%. Sensitivity, bad as bad, 17.18%. And specificity, good as good, 82.92%. And there is obviously a large difference between the in-sample and the out-of-sample performance, which suggests basically that the methodology or the method that is the model that is used here has been overfitted. So we have an overfitting issue here. Right, but anyway, this is the performance of one of the best models that is available out there. Right, in terms of the framework, as I said, plug and play framework. So for the in-sample classifier, we used EDAS, and for the out-of-sample classifier, CBR, K nearest neighbor algorithm. And this is the performance in-sample. So we can clearly see that it's a perfect performance. Honestly, I had to check and double check the code, and if it was not me who wrote the code, I would have real concerns here, right? But this is really outstanding, really outstanding. There is worse. When you get actually to the out-of-sample, we are still actually not misclassifying any of the good cases and almost not misclassifying any of the bad cases. Okay, there are slight differences here, differences based on the use of the distance, the choice of the distance matrix, metric, and these two are doing a better job compared to these. We have used other distances as well for testing purposes. So basically, it's fantastic, right? Question is, well, we have similar performance with TOPSIS and CBR. I'm not going to go into the details because of the time. And we have a similar performance with the double reference point method. And we have a similar performance with Vickers. So now the question is, how come? How come we are getting a performance like this? Well, I tried to go through different reasons, and honestly, the only one I found is my choice of the cutoff score. Because if we look at MCDM methods, actually I used all sorts of methods, and it seems like all the methods are almost delivering the same performance. So it's not really sensitive to the choice of the MCDM method. However, how the cutoff point is chosen is crucial. And this is the wrong thing that we are doing with other methodologies. And I will conclude here. Right, so eventually the challenge here, okay, with bankruptcy and distress, it has actually been tested. With credit scoring, it has not. So credit scoring people can give it a try or give me the data to run it for them.
Thank you, Professor Ouenniche, for this very interesting and stimulating lecture on the design of prediction models for bankruptcy, distress, and credit risk.